We at the Polar Geospatial Center use Parsl, and our main goal here is producing digital elevation models of the Earth. We started out with Antarctica, then added the polar regions, and then added pretty much all the land area in between. We're using an algorithm called SETSUM that's scalable and does the terrain extraction. But this is obviously a lot of data. It requires a lot of compute resources. If you look at it, we have like over 2 million individual tasks, and those tasks to create those get split into about 27 million DEM extraction tasks because the imagery we get from the satellites, oh, I should have said that, it's from satellite imagery. The imagery we get from the satellites is broken up into smaller scenes of an entire strip. A strip is like, I don't know, 50 kilometers by 200 kilometers or something like that. And each one of those scenes pairwise needs to get compared with the other scenes that it overlaps, and then SETSUM run on it, and then all those get put together back into the strips with an assembly task. We have a lot of repeat areas, which is good for looking at where there's change. Like I mean, a lot of the stuff we look at is like where ice is melting and or like icebergs are calving off. We can see like blowdowns in forested areas. We can see trees growing. We can see development and other things like that. But the big takeaway here is we're running lots of tasks that are kind of small. The resources we have available to us are generally HPC resources. Right now, we're primarily running on Frontera. And this is obviously a high throughput computing situation. So we're not running all 27 million tasks at once. That's been over many years. But at a single set, we have like between hundreds and 10,000s of these tasks that need to run at a time. This doesn't fit well into HPC systems. Our current limits are something like 75 jobs at once with a 48-hour max wall clock, and each job has to be greater than 2 nodes each. What we really want to run is about 4 tasks per node, which gives us the optimal kind of memory and throughput with the number of CPUs versus how SETSUM scales. And that gives us about 4.6 hours per task. And Parsl comes in because it lets us bundle all these tasks into these much larger jobs that we can actually submit to the Slurm queue. So this comes with a problem though, because not all of our tasks take the same amount of time to finish. And I think Dan Katz was the one that named this the long tail problem. But so we have jobs that finish up or tasks that as they finish up, they leave the rest of that reservation empty. And this isn't a problem like during the run because Parsl is good at like slotting new tasks in. And we have restarts turned on and checkpointing and stuff. So it's just fine. I mean, for us, it's pretty much fine if occasionally a task runs past the end of the wall clock and has to get rescheduled into a different Slurm job. So we just let that go. But at the end, we have like maybe a few dozen tasks left that are running, but each one of those tasks is holding up an entire, usually 10 node Slurm job. And so we can have a 10-node Slurm job with the, that is supposed to be hosting 40 tasks that has one task in it, and that's not optimal. The way around this is to have a lot of tasks per execution slot. Some modeling that I didn't do, but just kind of take the results of, showed that if we have at least 10 tasks per slot, we can maintain about 95% efficiency with that. But we end up with situations when we don't necessarily have enough to run because data hasn't come in quickly enough and we want to process results. And we also have issues with restarts between Parsl runs where some of the jobs failed and needed to be manually restarted. And then there's usually not that many. So in order to meet that 95% efficiency with the 10 per slot and the queue sizes and stuff, we basically needed to run 30,000 tasks at a time, which was problematic. Our solution to this is incredibly simple in hindsight, but wasn't obvious for us to do. So we thought we thought we'd point it out. We have kind of two knobs to turn. The number of nodes per block, which is the number of nodes per Slurm job, and the number of blocks, which becomes the number of Slurm jobs. We want to optimize for having smaller jobs because they better handle backfill, and they also release resources more granularity with higher granularity when at the end of the job cycle.
You'll be out of time.
Okay. So anyway, we iterate over the number of jobs or the nodes per block and calculate that. This is what it looks like looking at the combination of what's allowed from the Slurm queues. And the point here is that there's kind of a minimum and maximum number of tasks that fit in and will maintain that efficiency. When we look at minimizing the nodes per block, we get the second chart and see that we can now run from, down to about 40 tasks and still be okay. The net result here is we've increased the flexibility of the size of the job sets we can reasonably run. Restarts aren't wildly over provisioned anymore, and we're better neighbors on the HPC resource.